Okay, so we wanted to see that this induction has this sort of induction, the strong induction principle also has a basis. Without basis, things will not start, right? When we discussed the fifth piano axiom, there the basis started at 0. There is a statement just like this one, that one also had a statement Pn for which some conditions were given. The first condition is the basis, which is nothing but the statement that P of 0 is true. For the value 0 of n, the statement P is true. Now in this case, things are supposed to start at the natural number m0. So I want P m0 to be true. Just like in the fifth axiom of piano, I had P of 0 to be true. But in this statement, we don't see anywhere that P of m0 is true. In fact, something else entirely seems to be given. But from what is given to us, we can conclude that P m0 is true, like this. We first concentrate on this condition what is given to us. If Pm is true for all natural numbers m satisfying these inequalities, then Pn is true. What it really means is that if we look at these natural numbers, okay, until we get n, that is, we will get the predecessor of n. If I say like that, the predecessor of n is the number, is the natural number whose successor is n. Okay, if P is true in this region for these values of m, for these values of m, if P happens to be true, then P is also true for n. Right? Now using this, we want to conclude that Pm0 is true. Now let's look at this statement. Pm is true for all m satisfying these inequalities. Okay, so this is one part of this statement, the first part. Now in this part, if I replace n by m0, what is the meaning of this statement? Pm is true for all m satisfying this. This statement can be rewritten in a slightly different manner. It can be written as an implication, and the implication looks like this. If, or since I am writing it as an implication, let me not use if then. Although it's the same, but I want to use the implication symbol. M is an, or m is a natural number satisfying these inequalities. If m is a natural number that satisfies these inequalities, then I have this. Pm is true. You see, these two statements, this statement and this implication, they are one and the same. Whenever m is a natural number that satisfies these inequalities, Pm is true. Now, we are not saying anything about the truth of this implication. In general, when we have n, in general, we are not saying that this statement is true. If this turns out to be true, then Pn is true. That's what is given. But in this particular case, when in place of n we have m naught, but let's look at this statement, which is an implication. Now in this implication, this is the hypothesis. And what is the hypothesis? M is a natural number satisfying these inequalities. Is this hypothesis true? Let's look at the inequalities. I have m naught less than or equal to m, and at the same time I have m less than m naught. These two inequalities cannot be simultaneously satisfied. Why? Because of trichotomy. These two violate the trichotomy law that we have already proved. Okay, so the hypothesis is false. That means this implication is true, vacuously true. So the implication is vacuously true, which means that this statement is true. Although it's vacuously true, but it's true nevertheless. So what does this tell me now from the given condition? If this is true, then my hypothesis means what's given to me in the statement. Then Pm naught must be true. Okay, and this is nothing but the statement given to me when I replace n by m naught. So that's why Pm naught is true. So this way we can make sense of the beginning of the induction. Things start at m naught and then they move forward. Okay, so with this confusion out of the way, we can now start the proof of this strong principle of induction. Oh, by the way, this its proof has been asked in exercise 2 to 5. Okay, so this is not proved in the text, but we can prove it quite easily. There is a remark also before we write the proof. This will be remark 2 to 15. Now the remark just simply says that in practice, when we apply this strong principle of induction, usually we have these two choices. Either we start things at zero just like ordinary induction, although keep in mind that strong principle of induction has a stronger hypothesis than ordinary induction. So although things may start at zero, but it's still something else we are using than the fifth piano axiom. But sometimes m naught, the value of m naught can be taken to be 1. But m naught can be any natural number. Okay, it can be as high as 100 or 1000. M naught can be any natural number. So, but usually these two cases occur frequently. Okay, now we come to the proof. So although it's been asked as an exercise, but since we are going to write the proof, so we won't write solution. They are the same. Okay, so for this we are going to devise a new statement. So let Qm be the statement. What statement? This statement. Pm is true for all m satisfying these inequalities. Oh, sorry, this will be Pn. Okay, so Pn is this statement. that for a given n, Pm is true for all these values of m. That's what Qn is. We prove by induction that Qn is true for all natural numbers n. Okay, the use of by induction here means that I will use our ordinary fifth induction axiom, because that's what I have. I don't have this strong induction or any other induction yet. In fact, that's what I'm proving. Okay, so now we will realize why I am proving Qn and how this will help me. Let us just first go through the proof. First of all comes the question of Q0. When I have 0 here, no natural number is strictly less than 0. Why? In fact, we have seen this once, but let's just look at it once more. If I have a natural number m less than 0, right, then according to the definition or according to one proposition that we have proved previously, m has to be equal to 0 plus d, where d is a positive natural number. In one previous proposition, the one that we proved, which contained the reflexivity, symmetry, antisymmetry, transitivity, all those properties of the usual order relation among the natural numbers. In that one, the last subdivision, f, there we proved this. So, but then what, if we have this, then what is the conclusion? Since we know that 0 plus d is equal to d, so we get m is equal to d, where d is a positive natural number, right? So, but then what do we get? M is equal to d, right? M is equal to d. So from this we get d is less than 0. Now d is less than 0. I think I can conclude this quite quickly, can't I? Now I don't have to go through all these things. You see, we have already proved that every natural number is greater than or equal to 0, or 0 is less than or equal to every natural number. So if I now have m less than 0, then trichotomy is contradicted. Trichotomy is violated. So that's why no natural number is less than 0. That way we can conclude this. So what happens to my statement Q0? Q0 says it is this: Pm is true for all m or all natural numbers satisfying m naught less than or equal to m less than 0. So you see that this is again, the statement Q0 itself is again an implication, which says that if m is a natural number satisfying these inequalities, then Pm is true. And in this implication, the hypothesis is again false. So just like what we did or what we saw before starting this proof, this statement is vacuously true. So Q of 0 is vacuously true. So that means Q is true for n equal to 0. So the basis of my ordinary induction is ready. I have this. Now assume Qn is true for all. Oh no, not for all. True for some natural number n. Okay, so this is my induction hypothesis. That is, what does it mean? It means Pm is true for all natural numbers m satisfying this. This is what Qn being true means. Okay. Now, but what are we given? We are given that if such a thing is true, then P of the next natural number is true. Now, the condition given in the statement implies, so if all these things are true, it implies Pn is true. Here m does not take the value n. M takes all the natural number values starting from m0 but stopping short of n. It does not reach n. If P happens to be true for such values of m, then according to the condition given in the statement, Pn is true. You see, I have wrapped this place, but that contained that other part of the statement, the beginning part of the statement. So we now have, Pn true for all integer, integer, we still don't have integers, for all natural numbers we will develop integers and then only we can use that word. Pm is true, Pm true for all natural numbers m satisfying okay. Now, why have I written m equal to n separately? I could have included that here itself. No. But you may think that the proof is over because what is the what should I say? I'm not able to phrase this properly. In place of this past sentence, if I want to express this using Qn, what shall I write? I will naturally write that Qn ++ is true. I want to write this. Why? Because what is Qn++? Qn++ is the statement, let me write here. Qn plus plus is this statement. Pm is true for all natural numbers m satisfying this, right? So natural numbers m satisfying these inequalities start from m naught and end at n. So I have all the truths of Pm when m varies from m naught till until n. But I have the truth of P for additionally for n also, and that has come from here, you see. So that should be enough. But note that we have not yet proved that there is no natural number between n and n plus plus. That is, my variable m here varies freely between m naught and n. It takes the value n now. But who knows if there is a natural number between n and n plus plus. There is no such number, but we have to prove that, because the things we have proved so far, we have not addressed this question. That between a natural number, see, I am saying between, now I can say between because I have the order relation. Previously there was no between or anything like that. So is there a natural number that sits between n and its successor? The answer is no, but it needs a proof. So this Qn plus plus is true. I cannot immediately write this. Okay. So to complete the proof, I need to show that this statement is true. There is no natural number k such that k satisfies this, where n plus plus is actually n plus 1. Okay, this k does not exist. We have to show this. Suppose we suppose that such a k exists. Suppose, so we hope for a contradiction. Suppose there exists a natural number k such that these inequalities are true. Now let us look at this inequality. The first one. From n less than k, we have n plus plus less than or equal to k. And where is this coming from? This is coming from that proposition that we proved. I think part E. I forgot the proposition C. Proposition 2 to 16 or 12, sorry. 12 part E. That tells me that if a natural number is strictly less than another natural number, then the lesser one's successor is still less than or equal to the other natural number. But now n plus plus is less than or equal to k, and now look at this one, the second one. And k is also at the same time less than n plus plus, and trichotomy is violated here. Violate trichotomy. Okay, so our supposition is wrong. What was our supposition? That there exists a natural number k between n and n plus plus. So there is no such natural number k. Hence, we have this. Pm is true for all natural numbers m satisfying this n plus plus, because these inequalities are equivalent to these inequalities, less than or equal to n. The fact that there is no k between n and n plus plus allows me to write these inequalities like this. Okay, so now Pm is true for all m lying between m naught and n plus plus, excluding n plus plus. In other words, Qn plus plus is true. So by induction, Qn is true for all natural numbers n. Okay, so the beginning of the proof, we devised our statement Qn, and we have now proved that Qn is true for all natural numbers n, not starting from m naught or anything, but all n. But what is the benefit of this? Why did we do this? Now, you see, originally we have to prove that Pm is true for all natural numbers greater than or equal to m naught. Now here, however, we have a different statement Qn, but from this truth, from this part, we can conclude this. Pm is true for all natural numbers. How? Let m greater than or equal to m naught be a natural number. We want to prove that Pm is true. Now if we look at this, then from what we have proved above, Qm plus plus is true. Qm plus plus is true. How? That is because Qn is true for any n. In particular, if I replace n by m plus plus, that is also a natural number. So Qm plus plus is true. This means Pm is, what is the meaning of Qm plus plus being true? Pm is true. Or let me just write it like this. Let me use some other variable. Pr is true for all natural numbers are satisfying this. Okay, this is just simply the meaning of Qm plus plus being true. In particular, Pm is true. Why? Because m is less than m plus plus. So R has the value m. It can take the value m. So you see that for any m greater than or equal to m naught, we have proved that Pm is true. So that's how the strong principle of induction has been proved. Okay. Now this is very important, this principle. It will be used not only in analysis for proving statements but in many other places. Okay. Now there is one more thing regarding induction that we want to prove, that is the principle of backwards induction. So let's just clean everything and go to that. And this is given as the last exercise of section 2.2. So this is exercise 226. So what this one says, let n be a, let me create this line, let n be a natural number and let Pm be a property. Property pertaining to natural numbers. Right, such that there is a condition such that whenever Pm plus plus is true, Pm is also true. Prove that Pm is true for all natural numbers m less than or equal to n. Oh, I haven't mentioned one more thing. I forgot to mention, before this proof that there is one more condition. Sorry about this. Let Pn be true. Because the induction, although it's in this case it's going in the backwards direction, that also has to start somewhere. So it's starting at Pn and then it goes to P its predecessor, then P of that who's that's predecessor. So it goes until it reaches P0 where it stops. So unlike our usual induction or strong principle of induction, things do not go on indefinitely. Here we have finitely many cases. Okay, nevertheless, so we need to solve this. So solution. And here also, just like the proof of the strong principle of induction, we will devise a new statement. Okay. Let Qm be the statement. Actually, it's the statement that all the things are true before n. I forgot the statement. What is the statement? Let me know. Okay. Let Qn be the statement. Let me write it here. If Pn is true, then Pm is true for all natural numbers m less than or equal to n. Okay, this is the statement Qn.